Okay, welcome after the lunch. We have another panel in front of us. Anirban unfortunately got sick on the way here, and he couldn't join us in person. So he asked me to run this session, and I'll try to do my best. So here we're going to talk about, if I knew then what I know now, I would have never designed it this way. A very interesting session, looks like. Approaches to CI conceptualization and design. I know Rob was helping also with gathering this panel. Thank you, Rob. And, Anirban did some slides. I tried to speak to them a little bit. So the first slide shows all the NSF investments in major facilities, in basically any domain you can imagine, right? And these facilities, as we know, we have many of you here, have their challenges and provide services to large scientific communities globally. And we would like to see what kind of challenges and how they map to the data flow. We know that we can imagine that any of these technical operational collaborations, technical challenges, will have some impact on a step or more steps in our data lifecycle. And also about for sure the impact on how we design the infrastructure to manage data, collect data, manage data, and compute on them, and then provide them to scientific community. And also the major facilities life cycle that is very much connected to the investment cycles, right? Has these phases where we have the points of influence for the CI conceptualization in every of these steps. I know that many challenges that the major facilities have, for example, make it hard for them to give their staff time to do research, to come up with new ideas and so on. So we would like to hear from you about all these challenges and on one thing, but really, what you have learned as you went through conceptualization of CI and what kind of wow moments you have today or you had on the way, and how you approach these cycles in a different way. So we have some questions for the panelists, and we asked 4 panelists to come with some presentations speaking to these 3 questions. What were some unexpected outcomes of CI design during planning, design, construction, or enhancements, which were discovered during deployment? And what are the top lessons learned from that experience that might translate to the broader community? What are some of the best practices for involving the community of major facilities users to glean the CI requirements during design, construction, or enhancements? And what were the major steps in the CI conceptualization and design process? Okay, our panelists, Sabine Botha, Frank Wuerthwein, Dan Stanzione, and Rob Casey, they will give the presentations. Again, welcome our panelists. Thank you. We would like this session to be kind of lightweight, really be open. I think serious, but not too serious, and try to really kind of tell us your stories and both panelists, and then we're gonna hopefully hear also from the audience. So let's go with the first presentation. Now, what I do here? Rob, you're gonna go first.
So, Ms. Yeah. So hopefully I don't have too many slides, but yeah, this should be a really interesting session. It'll be kind of like a little bit of honest confessional to a certain extent. This is kind of that. I'm hoping it'll be a little lighter moment now. We're getting towards the end of the second day post lunch. We'll try to keep things light. So this is just a brief coverage of the adventures we've had in merging 2 major facilities in the cloud. And so just to retread over what I was alluding to this morning, we have 2 major facilities that EarthScope operates. And so GAGE operates Geodesy the Geodesy Research Major Facility, and SAGE is the seismology major facility. And so we incorporated as EarthScope, UNAVCO, and IRIS last year, and we have now reached 1 year of being incorporated as this new entity. And the goal is for us to bring forth a new era of interoperable and highly scalable services in support of a new frontier of geophysical research. So the CI plan, the component I was most closely associated with, was to migrate our on-prem facilities entirely to the cloud. So this pictograph kind of represents the sort of, hopeful environment that we all experience when we get started with something this ambitious. There's a lot of people that you bring together that come with ideas, and they introduce these, and we start to see the possibilities of what could be. You go forward a year or two, and now that we've actually done some of the practical work, you start to look back at what you've put together, and it's sort of here and there. This is an example of a Rube Goldberg machine. It's certainly a slight exaggeration, as we've been able to stick somewhat to plan, but it's not too far off in terms of compromises we've had to make along the way. So the steps that we followed initially were design, and then we kind of followed up with implementation. So we developed a vision and gave it the project name, the Common Cloud Platform. A lot of times we'll refer to it as the CCP. And then we identified major tasks and applied leadership to each of those major tasks, and then had a kickoff meeting. And so we started off with big vision and kind of big design plans. We also engaged with key stakeholders. We selected a number of individuals that we wanted to gather requirements from, and had a number of requirements that we ended up pulling in to help us with our initial proposed design goals. We brought in CI Compass as our cyber infrastructure efforts, so thank you. And they advised us in the process of doing the design and getting started with the development. So documents that we ended up producing, we refer to as the concept of operations. And then a little more detailed was a requirements document. And then finally getting down kind of to the nuts and bolts is design documents for each of the major components. And then we set up the implementation teams to actually carry out the first prototypes. The community involvement involves senior users. That this was kind of a term, I believe we pulled this from the Prince2 project management model. So that's a term you use for stakeholders or experts that would help to identify what are the important use case stories for a given system. And in this case, for this cloud system, we ended up gathering and documenting about 24 separate use cases that highlighted scenarios that we wanted to be able to see the system perform well at. Those use cases were then incorporated into the concept of operations document. GAGE and SAGE also connected to the community by holding joint workshops. And we introduced some of the cloud platform concepts that were taking shape, and allowed the attendees to respond to those and offer their observations. And then we've been putting out announcements to the public, generally electronically, describing the Common Cloud Platform concept and kind of where it's the stage that it's at. So time passes as it does, and not everything goes entirely to plan, but you keep on trying. So we get to the lessons part in cloud development. And this is like after we've had about perhaps 1.5 years worth of actual systems development. The things that one of the lessons that's a big one, I think, is it's better to at an early stage identify where your cliffs are in the migration timeline. And we've been caught by surprise in a couple of cases with this. So if a data facility is on a limited time lease, this is a time where you may no longer have that facility or the equipment that's within it. So this represents a hard timeline for certain aspects of your migration. End of life for equipment. Computer systems do wear out. Support for those systems also become progressively more expensive, or they just cease to exist after a certain point in time. Software license expiry is also something to consider. There's probably lots of examples that you can imagine, but those are good things to pinpoint because that helps to establish what time frame do I have to work within to get to my goals. It's good to select a cloud platform or vendor before you design. Basically, the experience we ran into is we started with cloud agnostic designs and really with the intention of being to where whatever we built could actually be deployed to multiple clouds. What we discovered was once we had a vendor that we realized that our designs were going to be operationally much more expensive and tedious to maintain than going with vendor specific managed systems. And so as a result, we had to rework quite a bit of our original choices of technologies and kind of relearn some ways of doing things. You have to be agile as you go along. You got to be prepared to pivot from system refactor, which is kind of like where we're actually imagining a whole new design for older systems. And if you're starting to run into a cliff, as I allude to above, you might have to rehome some of that system, just picking up the virtual machine and moving it. So yeah, this is an alteration of the plan that can represent complication if you're already in the process of building a new system, and you have to be able to ask yourself, can you design your greenfield workflow and have it run alongside a legacy workflow and still have continuity of service? That's a complication you can run into. And finally, I think a really big message here, just to be a realist, is implementation reality eats big upfront design for lunch. Kind of my personal viewpoint looking back in terms of when we set out to design and come up with the plan, we probably spent more time doing untested designs before we actually got to practical implementation. And there's a lot of what we ended up designing that ended up getting thrown out. I think the concepts were right, but we spent a lot of time on details that we ended up not being able to make use of. So it's actually better to try to encourage getting past the big upfront design point and get onto your target platform, have that identified, get coding and document as you go. And so this is a little more of an agile approach to building a major system. It doesn't hurt to have a high level plan. In fact, that's really good. You want to have kind of that general roadmap of how to get across, the US. The Griswolds had some sort of plan to get to Wally World, right? So, and as they discovered, it did not go to plan. And so you have to keep adapting. So, success as the cloud takes shape. So as you're starting to build out the system, train your team to think in cloudy architectural principles. And so really rethink your approach to things that might have otherwise resulted in a monolithic design. Seek out the standards that you already have and look to other standards that are widely accepted. And around this, you can align your data, code, and processes. You want to maintain a clear vision that is shared with the team repeatedly. And so this is something that management has to do in terms of always keeping people's eye on the ball that's ahead of them. Use encouragement and mentorship to drive away fear and doubt, because you will hit that trough of disillusionment, probably more than once. And so it's incumbent on everyone to encourage people to keep going and keep moving forward and be willing to take the time to teach each other what you've learned. Establish and enforce deployment and access security. So this is when you're building out a new system, you're probably building out a new deployment architecture. This is the time where you can make sure that your source code pipeline is made secure and that the systems you deploy to are secure when they go to the production area. Utilize what the team has already built. A lot of times you'll be bringing over technologies that are well accepted, libraries, and other modes of working, work collaboratively, and don't just reinvent the wheel just because you have the opportunity to work on something new. Try to make use of the tools you have at hand. And then monitor and observe your deployed resources. So this is a big thing with the cloud. It's a lot more invisible to the operational people if you don't have a way to monitor all of the complex things that can happen in a cloud system. And so finally, the philosophy I like to take is just like with large scale computing, is you want to think big and you want to think multitudes. This is going to the cloud is a whole new way of thinking about how you maintain a system, in that you don't maintain gingerly a number of servers and they're all kind of tweaked and so forth. You actually want to think about how quickly can I spin up 1,000 instances of the same thing, have it to its job, and then disappear, just bring that bulldozer through. So those are the types of things you need to think. And that's it.
Thank you.
So thanks very much for the invitation to speak. I can only assume, based on the topic here, that, given that the panel topic is how have you screwed up in the past, that we were selected as the people the community thinks are the 4 most likely people to have made catastrophic mistakes in the past. So I certainly then understood why I got my invitation. So the makes perfect sense. I was perfectly prepared to respond to that. So so thank you very much for your continued confidence in what we do. So yeah, so I represent in the PI for the leadership class computing facility, and where we are in the long design process is that Jarek sort of gave the overview of, is we passed final design last spring, which means, of course, when Congress passes the budget on time on October 1st of 2023, we get our official start for construction. Obviously, that's going swimmingly, because now maybe March 8th of 2024, they'll pass a budget. We are in the budget language, so perhaps this will start soon, but we're in that fun part between you're finished with design, but have not yet allowed to start construction. So I think one big contrast with some of the other facilities is we're pretty much all CI. Instead of it being a small component, we're to do leadership computing. That said, even in building big computers, the trick is where you put them, right? So almost half the money in the TPC for the construction phase is actually acquisition of the data center, right? Coming up with 20 megawatts of power and liquid cooling to handle 150 kilowatts per server cabinet. It's about as wide as this podium. So we are higher per square centimeter in cooling density than nuclear reactors at this point. So, so our major components in the spend are, the physical plant, a couple $100 million, compute and storage systems, like 150 million, and then all the people and software stack around that, that we need to build out. So, so unexpected outcomes, the surprises along the way. First of all, the process is, did I want to do this one first? Yeah, look, let me start on this slide. I'll come back. Pasted them in the wrong order. So I will say our most surprising shift from conceptual to preliminary design was our data center strategy. We spent conceptual design thinking about on-premise built, an on-campus build. We've moved to a co-location services agreement, which I may also still live to regret, but being in the monopoly for utilities that where our campus sits and dealing with the incredible construction increases in Austin and particularly on campus, it ended up being $70 million cheaper to not build the building ourselves. So that was a huge change from conceptual to preliminary. The fortunate thing, which is becoming the unfortunate thing, is we've gone from a data center building boom to an AI data center craze in the last years, where we're building more. There are more data centers under construction than exist in the world right now. So, in 2 years, we're rebuilding 50 years of data center capacity. But but because of that, there were multiple facilities being built within 8 miles of where we are. So near to our staff, with timing that allowed us to customize as they built the buildings. And if we didn't have those advantages, we could have never gone into a regular colo facility. So, so that was a fairly surprising shift. So I feel like I've deleted a bullet here too. I will say that doing technology planning 8+ years in advance, as mentioned in the research ship stock this morning, is a entirely futile exercise. So we wrote plans that I just knew were nonsense way back when. So an example of that is the original proposal for what became this facility went in 2017, which is a pretty tight timeline by large facility standards. But I'm pretty sure that if the word AI was in there, it was maybe once in the entire proposal. The world has maybe shifted just a little towards AI in the past 7 years, which just changed all of the computer requirements. So yeah, in a slide in December presenting the last milestone to the board, LCCF was listed as the cornerstone of the NSF NAIR investment. So it went from being not at all about AI to being the cornerstone of the AI investment at NSF. So all during design. So that's fun. Every vendor roadmap was completely wrong. Just as an example, Intel was twice the size of NVIDIA by market cap when we started. They're now 1/7 the size of NVIDIA. Part of that is because NVIDIA is much larger. Part of it is because Intel is much smaller. So, I mean, just massive shifts there. The only good things is that we were able to reasonably extrapolate our power and cooling requirements, and those, the system ones have gone up and down, but they're all in the envelope of the 15 megawatts we're building out initially. Everything's going to fit nicely. So you could sort of say, look, we don't know what the chips are going to be called. We don't know exactly what they're going to do, but I can graph for 20 years the power and cooling demand increases. And although they've sped up some, we're still within the margin of error on that. So, and to do that, I had to not believe anything that NVIDIA, Intel, or AMD told us on power, because they were all off by a factor of 2 versus where they are. So, yeah, and I mentioned all the leaders in the industry are completely different. It turns out all the people are the same, but they all have different jobs at different companies, right? I know 15 people who've moved from Intel to NVIDIA in the last 5 years. There have been hundreds. And some of them are through several companies since then, right? The storage vendors have changed. We're buying our interconnect from NVIDIA. They weren't in the interconnect business in 2017. So, you know, another thing that hadn't changed is this trajectory on using the cloud. Cloud hasn't really changed for us because we use the machines all the time. They continue to shift towards on-prem facilities. This came up this morning, but I mentioned it in the Q&A, but cloud prices have effectively tripled, and more than that for AI. I used to price what we delivered. I did an analysis in like 2020 where I figured out just the compute time on CPUs that we put out at TACC was worth about 120 million of Amazon time per year. I did it again in December and it came out to 418 million, and we do about the same. And we're spending 35 to 40 million to deliver that, including people. So it's sort of 11 to 1. And that assumes that all storage in the cloud is free and all networking in the cloud is free, and that there's no people costs associated with going to the cloud. And if you believe all those things are true, then it's only 11 to 1 per year. Yeah, we delivered $418 million of, oh, and I left out all the GPUs because the GPUs are astronomical, right? It would have been at $1 billion, but yeah, $418 million just in hours of CPU per core delivered. So yeah, it's really worse, but nobody believes me when I put up the bigger numbers. Did that one. So last one on just sort of things that have changed. For what started as a leadership computing project, which typically means solving the really big computing problems. I admit that even early on, we spent a lot of time thinking about the data lifecycle. And we've added a lot of pieces to design around that. You know, again, technology shifts. There were a lot of spinning hard drives in the original design. There are now none in the current design. But in retrospect, this needed even more attention than we gave it, because what have we talked about for most of this meeting and at least 50 other workshops we've all been to in the last 7-8 years? Long-term data, where do we put it? How do we retain it? So we have facilities for that. I wish I'd put more, particularly on the people curation side, into the design there. That data shift and the shift towards AI has also changed computing modes. So there's a lot more interactive computing, a lot more persistent services, and other things that I would call not leadership computing modes, but I've convinced NSF should be within our scope. You know, hosted services. And we had put that design in the hardware plans because the extent we could see them coming, but it turns out supporting all these sort of smaller curated data sets, smaller interactive things, the support costs are a lot higher than just running 100,000 core simulations over and over again through a batch queue. And I didn't really anticipate the people costs well. And then part of that was the thing that got mentioned yesterday several times was I think some of them by Frank, was that the ECSS or the Extended Collaborative Support Service used to be in the NSF computing ecosystem and Exceed. It was 40 FTEs and all 40 of them went away. And that's something we probably should have compensated for a little more in our planning, but that decision was made 4 years after the planning process started. So it was sort of hard to anticipate that NSF was going to shift that along the way. So there's one that eventually amounts to what are the best practices in doing this? I would say that as always, the best practice is to never underestimate the demands of the MREFC process. That's an easy thing to do because I'm not sure it's theoretically possible to overestimate the demands of the MREFC process for those who have gone through it. So I spend, I think, more on project management costs per month than we did on the last $300 million in systems combined. We also had a lot of users generating requirements early on, particularly when we formally launched conceptual design in 2019, have a bunch of workshops. They were mostly wrong. Almost everything the user said was totally inaccurate. Again, since we pulled from mostly the leadership computing users in the past, there was almost no AI in the workloads and nobody talked about AI at the workshop. And therefore 2/3 of them were like, don't buy GPUs. We can't use them. They're useless. And now we're buying 4,000. So that was obviously really good advice. But what comes down to is getting broad trends and directions from talking to groups of users about sort of where they're going with their science was useful. If we'd listened to the details, we would have built a great system for 2020 and deployed it next year. It would have just been completely misaligned with where needs are. And that leads me to the other one, which is basically trust your gut. Turns out, like I said, I'm the PI for the project. Theoretically, there's a reason for that. And if you're PI in any of these facilities, you probably know more about it than anybody who's going to come in and tell you what to do. From reviewers, NSF auditors who believe that they're the source of all knowledge in cost because you spent 15 cents misplanning travel that you're going to do in 2028 because we control airline prices in the future. The AIs really do. It's fine. But I found that every time I caved to a panel or various offices at NSF, I always ended up regretting it when my gut feeling was to not do that. And I wished I'd pushed back harder years later. Because for starters, most of the issues they cared about 5 years ago are not the issues they care about, right? Every question I get is AI, right? Out of NSF now. None of the questions were about AI 5 years ago, just again, as one of many examples. It was power costs, and now they don't care at all. They're so small compared to everything else. So you have to believe in your team's vision of the future for how your instrument's going to be used, how the science is going to play out, et cetera, and not necessarily what the past data says it will, because things change. So again, couldn't do rationalize an investment in AI based on any historical data that I could give to a panel or an auditor. Yet, should I not invest in AI? It's sort of a duh thing at this point. So we're the subject matter experts, and sometimes we need to act like them and not just fight the audit question based on graphs. So just last thing I want to slip in is while you're waiting for us to actually stand up the leadership class computing facility, because funding is delayed, we have lots of bridge systems that will be available shortly that NSF pays for. We actually at this point have a major platform with NVIDIA, with Intel, and with AMD. So you can pick your favorite among Stampede 3, Vista, and Lone Star 6 that are all currently available. The Vista, which will come online in March. I was looking for the ship carrying it out here to be unloaded in Long Beach, but because it's somewhere in the middle of the Pacific Ocean, but it has 600 Grace hoppers that are going to be in it. The NVIDIA new GPU combination with CPUs. Again, hope to be done with it by March. So, certainly available to everybody by April. But we also have a brand new Intel system coming online. We have an AMD system we brought online last year. The archive and online data systems will be replaced with new hardware when LCCF starts, but they already exist with their current hardware. The old Frontera system still has 500,000 cores. Admittedly, 300,000 of them were running 3 jobs this morning, but 300,000 core jobs. One molecular dynamics for a bio application, one astrophysics simulation, and I actually don't know what the third one was. I couldn't tell by user ID, but also, if I refer to you instead of by name as like TG865, it's because I know everybody by their user IDs on the system and not by their actual identities. I don't know them by ORCID IDs yet, but I'll work on that. So I have an ORCID ID, but yeah, but I know them by user IDs on the system. So please don't hesitate to reach out. One benefit of this meeting is we already solved the problem for IceCube while we're here, based on a chat yesterday. So as Benedict mentioned this morning. So yeah, we're out here to help. So I'll stop there. Thanks.
And I think that I want to start with by the main take-home message. I talk about the LHC, and I think that the number one lesson learned from making that program work is that focus on time invariant characteristics of your science. Because if you focus on anything that is at any moment in time, trendy or fashionable, you're going to be 100% wrong. Just like I then said a few years later. To make my point, in around 2000, so the LHC started running in 2010. Around 2000, CERN thought it was all going to be run with Windows NT, and it will all be run on a data infrastructure based on objectivity, a company nobody in this room probably has heard of. So, okay, fine, a few. Basically, they're defunct. And they're defunct now for 20 years, almost 20 years, because they went defunct in 2002 or 3 or so. So bottom line, and the way that things work is you focus on the fundamentals that you know will not change. And those fundamentals then drive you to a decision-making process on architecture. And then you go to town and develop an agile, I call it a verification and a schedule, where every couple of years you go through a large scale, ever-increasing scale exercise to verify that the things that you're putting in place over the 10-year timeline are actually working at the scale that they're supposed to, and have a fighting chance in how to work at the scale that you have to get to. This is what we effectively did before 2010, and this is what we're effectively doing now as we're heading to another factor of 10 for the High LHC in 2030 or 28 or whatever it is. And I wanted to give you 3 examples of the kind of thinking that is involved. And the first one is that the LHC program is a multi-generational global enterprise, meaning it's something like 50 years or so that it takes. If you take it really literally from design process until it gets mothballed, it's probably 70 years. And so in addition to being multi-generational global enterprise, it's a global enterprise. There right now, I can't remember, but something like 200 plus institutions. I think it's 250 or so at this point, just in the CMS experiment. It's across more than 40 countries, I think 44, 45 at this point. And it's for more than 50 years. And so that in its own right is a fact, and it will never change for the entire 70 years of the LHC program. So you should design yourself around making things work with that in mind. The second fact is the accelerator is about to provide order 10 to the 11 mutually independent beam crossings per year. That means you have an awful lot of pieces, none of which have anything to do with each other. That also means that the compute time or storage volume per piece must be minuscule. Otherwise, you run out of budget instantaneously. And that means ultimately that you actually do not require anything that is anyhow in any way, shape, or form depending on low latency anything, because you parallelize it beautifully by design. It's just always parallel because the pieces don't depend on each other. And once you realize this, then you can start designing something that will actually work. And the third one is the data produced is immutable. And I believe that this is true for very many facilities, because we all have in common that we create data somehow, and then it's better never changing. It is better totally understood what its provenance was, And nobody wants it to change because it would be a pain in the ass to understand what has changed. And immutable data has a beautiful feature that exists no use case for read, modify, write. If you design a storage system for immutable data, throw away cache coherency out of the considerations first. And that again means that parallel file systems are basically irrelevant. You don't need a parallel file system. It has no use because there is nothing that has to depend on each other. And that is actually, if you look at the main difference between the kind of file systems that Dan or I, as directors of a supercomputer center, have to deploy, and the file systems that Fermilab or CERN deploys, they're fundamentally different for that simple reason. Because Dan or I have to support simulation people that do this, read, modify, write all the time, whereas the LHC has none of this. And so now I basically set my entire talk at this point, but I want to dig in a little bit more. So multi-generation global enterprise, optimized architecture for in-kind contributions. Most people who look at how the LHC does its business say upright, you must be crazy, because we actually literally distribute our computing around the world. But it is actually really essential, because nobody wants to send, if you're not a crook, then you don't send money to Switzerland. That's just fact. Because the only people who have money in Geneva are crooks. And so basically the world's national science foundations out of all nations would much rather spend their money in their own countries than send them anywhere. And so in-kind contributions in a social environment like ours are everything. Next, optimize the architecture for openness and expandability such that people can live anywhere in the world and still participate meaningfully. In particle physics, the LHC is the first program where the host lab is the first order irrelevant, meaning when you think about people, because the people you need to run that program are not permanently at the host lab. They're just not there. And so you need to develop structures, and you need to develop means that people can live at home with their families and don't have to relocate to Geneva. And that it provides certain constraints and also provides certain technological constraints in order to optimize for that in some way. Then the next one, today's friends are tomorrow's enemies, or vice versa. And there is literally, I asked myself, can I come up with any conflict that is current, past, or future, and find one where the people in that conflict, national state conflict, are not working both at the LHC, and I can't. Whether this is Russia and Ukraine, Iran, and most everybody else in the world, Israel and the Arab states, China and Taiwan. North Korea has not bombed the LHC. So voila, we saved one. So India, Pakistan, take your pick of potential future conflicts or past conflicts. They all work at the LHC. So amusing anecdote, the LHC community went through a major soul searching and discussion after the Russians invaded Ukraine on whether to throw out Russian collaborators. And we had a period where we agreed to not publish a single paper until we had figured out what the author list would be like. So these kinds of things, and the reason why I'm saying this is, as much as I would love to have all computing taken care of by a single country, preferably the US, and preferably at one location, preferably here or my center, it's insanity, because we were not allowed to be collaborating with half the people on the collaboration because they come from countries that in one point or the other, the US doesn't like. So how do I deal with a situation where the US doesn't like China now and doesn't like X tomorrow, and yesterday didn't like that country, and it changes all the time? I have CERN. anytime I'm not allowed to work with country X, I send them to CERN. CERN is a non-country entity. It's a UN entity by design, and they are allowed to work with everybody in the UN. So it's structures like that that are really, really important when you're doing something like we do. And then the last one here is try to avoid hiding fundamentals behind project-specific tools because your workforce is transient. And this is maybe I'm not going to make friends here, but large facilities have large budgets. That's just true, and rightfully so. But what we all do then is we over-design our interfaces. We make them so easy to use, supposedly easy to use, that they have no relevance to anybody else anymore. And so the students that we educate don't have a freaking clue how anything works. And that is a huge disservice that we give to our students because they can't function in the real world where they use common interfaces that everybody else uses. And that is a mistake that most of the large facilities tend to make in some capacity or the other. And the LHC is a prime contender for having made that mistakes many times over. For my own research group, where I actually do things myself, given that we have such a large capability in CI, we don't use the experiment provided submission infrastructure. We use what the rest of the community uses instead. And we build on that, because that way my students have a fighting chance to develop a skill that is actually useful. And so, and that's the kind of thing that also comes from the multi-generational. Then I think I said all of this, paralyzed by nature, it's not, I covered everything. Immutable, I want to dig in that a little bit. If you look at something like the CMS experiment, it produces official data sets for the collaboration. And within the collaboration, it actually is all according to FAIR principles. We just, for political reasons, don't allow the rest of the world to see our data. And I'm not going to go into this. I can talk to you privately. But it means that fundamentally our structures are actually comply with FAIR. They're just policy constrained to FAIR with us rather than FAIR with others. Then data is written locally, committed to archive after a file is closed. And the moment a file is closed, it becomes immutable. It has every file gets a checksum, and that checksum is law. If a file ever does not comply to the checksum, it gets deleted from disk because obviously it's not the right file. It got corrupted somewhere. And we do this routinely, meaning this sort of thing happens. And that is the degree to which immutable is important. What this gives you for free, it massively simplifies global data infrastructure. So we couldn't actually build a global file system, quote unquote, for the LHC because there's no cache currency required. The speed of light is irrelevant. It can all be parallel and independent. And I think that's it. Summary and conclusions, we're all influenced by fashions of our trade. It's therefore important to remind ourselves what's really fundamental to what we do. Initial designs as well as change should be grounded in the time invariant characteristics of your scientific enterprise, because the time invariant characteristics, they actually are time invariant. They don't change. And then large projects have large budgets and thus have a tendency to produce bespoke interfaces and tools. And that's a disservice to the young. Thank you.
Well, thank you for the organizers for asking me to join this panel. I'm not sure what happened to my ASU logo there. That's supposed to be the ASU logo in the bottom right corner. So please use your imaginations. And I actually used my imagination when I was wondering why I was invited to speak at this panel. And I kind of see two people from Compass CI in a room, and one of them goes, "Who's that person? Why are they on the list of attendees?" And then the other one said, "I don't know. Let's put them in this panel where she can tell us about everything she's done wrong." And then we'll know who she is afterwards, hopefully. So that's what I'm going to do. And I'm actually going to give you a bit of a different perspective because I'm actually coming from the user side and I only just switched over to the actual development and design side. So I'm going to tell you how I have brought facilities to their knees by terrible things that I did as a user. And hopefully you will learn from that. And so a little bit about the project that I'm working on now, this compact X-ray free electron laser source that we're building at ASU. A free electron laser, it's kind of light source. It's unique in the sense of that it makes really bright, really short X-ray pulses. And we're talking of X-ray pulses of around a femtosecond, couple femtosecond, few hundred femtosecond scales. This means that everything we do is incredibly fast, and the processes that we can look at can be incredibly fast because we can probe them that quickly. So we have all kinds of applications for this, ranging from medical imaging, protein crystallography, photosynthesis, chemical catalysis, attosecond physics, laser science, condensed matter, all of these things, a lot of things I know absolutely nothing about. But all of these people can come and they can use the source and they can do their experiment. There are some of these sources around the world, so free electron lasers. As some of you may know, there are major facilities. There's one in the US, the LCLS at SLAC. There's then a couple more that I'll show you in a second a bit more about. And these are kind of the ones that I'm going to talk about because those are the ones where I know what I do as a user. And oh yeah, the special thing about the compact one that we're building is where these facilities all have their 100-meter long accelerators. Ours fits in the basement of a building. So that makes it compact, or as we call, benchtop. For the CXFEL, one thing I didn't mention is we're actually building two light sources, the CXFEL and then the CXLS, which is the hard cousin of the CXFEL, by which I mean the X-rays are actually hard, whereas the CXFEL is going to be soft. And that one we've actually already built, and we're about to start commissioning it. And that's the one that's kind of our guinea pig for everything we're going to try out, because the NSF paid for the CXFEL. So the NSF is kind of very happy that we have this little guinea pig to play around with, learn from, and then implement everything for the CXFEL, which is then going to be the NSF's supported facility. We're anticipating to have data collection rates of 100 kilohertz, and this is simply because of how quickly we can produce these X-ray pulses. We can produce them at a kilohertz rate, so that's how quickly we're going to have to collect data if we want to use the short pulses to probe things. We're anticipating about terabytes of data per week that we're going to be collecting, which is a lot. We have a lot of detectors. Like I said, a lot of experiments, different kinds of experiments I know nothing about, detectors I don't know, I've never worked with, that we somehow need to integrate and catalog them. And especially because we do a lot of time resolved studies, because we have this really short X-ray pulse, we need to somehow time tag every single pulse and every single image related to that pulse and every sensor output related to that specific pulse, which is what we're currently trying to design. And then, yeah, we also want AI-guided real-time optimized data collection, because that's, as I think some of the other people already said, the trend currently, and you go with the trend, right? So a bit about my background and why I said that I'm going to give you more user stories, and hopefully you can learn from them, is there was this science and or it still is, this was a science and technology center from the NSF called BioXFEL. And this was, I don't know, what do you say? It was founded back in 2014. And the idea was simply that we have these new X-ray sources. And we discovered that they're really good to use for certain biological applications if you want to do time resolved studies, but biologists don't really know how to cope with this kind of data amount, with this kind of data processing that you need to do. So let's form this center where everybody can work together to work on the hardware, the software, and by hardware I mean simple things like also introducing the sample into the beam, and things like that. Form the center, and then we have expertise that can go around from one institution to another and help one another and hopefully further this field. And they hired me back in 2019 as their data support scientist, which means anyone who was in some way related to the center or one of these research institutions could call me up and say, hey, I have an experiment. I don't know how to look at data. Can you please come and help? And that's why I've been to a lot of research facilities, use their computer, their cyber infrastructure, and also around the world. And things are actually very different depending on where you are in the world. But yeah, before I get into that, I just wanted to, quote myself. When I work with students and things, students often say, "Are you sure we're allowed to do that?" And then I say, just do it and see what happens. It's easier to ask for forgiveness than permission. And one other thing that I may or may not say at times is, what's the worst the facility is going to do? Send us a harsh worded email? And that is because working as a data scientist, you feel very anonymous. You feel like you can hide behind this wall of cyber infrastructure. And yeah, who's going to hold you accountable for it, especially as a user, right? Because you don't even work for the facility. The facility can't even fire you if you mess up. So that leads me to some of the things that we've learned. So first, a bit more serious on the facility side. We learned the hard way that you need redundancy in personnel knowledge and documentation. And this is simply, we're a mid-sized facility. We're not a large facility. We don't have this huge budget. So a lot of knowledge or even documentation locked up in a single person. Something happens to that single person, which unfortunately happened in our case. Yeah, it's gone. It needs to be redone, which kind of sucks. Don't overpromise, especially to scientists, because scientists are very imaginative. They remember everything you promise them. They ignore everything you tell them that they don't like. We're currently in the process of scoping and documenting what our data retention policies are going to be. And this is really difficult because, like I said, we have all these different people from these different areas, and they all have different ideas of what it should be. Biologists, for example, believe keep everything for forever. We're not sure we can do that, not with our budget, but we're trying to figure it out. And the other thing is, if you work with a particle science student, they can usually do a bit of programming. They understand some physics. If you're with a biologist, I very often literally get the sense I don't do data, which means they show up with a test tube of protein solution, and then they want the protein structure out. And they don't know how to get there. They don't care. And that's kind of a bit challenging because, like you said, you don't want to give tools that do everything for them because they need to learn. Yeah, it's a bit hard if they're refusing to do that, but yeah, that's a different different story. Another thing that we have is find a solution to a problem and not a problem for a solution. What I mean with this is this beautiful AI optimized data collection. We want to use AI to do optimized data collection. What is optimized data? We don't know. When I asked the AI guys what they were going to optimize, they say, we can do anything. Just tell us what we need to optimize. So yeah, we're trying to, find the problem that we already have the solution for. And one other thing is give credit where credit is due. And this is simply because I feel like, especially from a facility side, a lot of work goes into this and people don't know because it's exactly this anonymity of having the cyber infrastructure. You don't actually know that there's people behind there that are working really hard to make it happen. Now for the user perspective, I did actually check the attendee list to make sure that no one from the major facilities that I use are here. Passwords and accounts are shared across user groups. Yes, I know we're not supposed to do that, but I'm pretty sure most people at some point had a PI that said, I can't get into my account. How am I supposed to read the logbook? I'll log you in and then they read it through your account. And yeah, we do that. So be aware. The main takeaway message from this, at least what I'm trying to do now, we're thinking about how we're going to implement safeguards against this, the CXLS, is that everybody that's kind of in contact with one another regarding the same thing, well, if they have the same permission, that shouldn't be too bad, right? And the next point, this is actually really interesting. It's the harder the safety training, the more memorable, because I don't think we ever talked about this, but when you go to a major facility, you usually spend a day doing safety training first, right? Cyber safety. You have to have your cyber safety security updated once a year, depending on where you go. I can tell you from the LCLS Slack, I know absolutely nothing from what's actually in their slides because I clicked through them on the side whilst doing something else. So ask me for the emergency number that I need to call if someone falls over, no idea. Now the European CXFEL, I had to repeat the safety training 3 times. And I then had to cheat to actually get through because they have this map where you have to click exactly where all the collection points are when you get evacuated from the building. And when I say click exactly, I'm exactly within a few pixels. So in the end, I had to take a picture of the map so that later where the quiz was, I knew exactly where to click so that I could finally finish this. The good thing is I know where the collection points are. And even if I didn't, I have a picture on my phone in case I need to check where to go. And this is actually, I think, a cultural thing. How do I put this nicely? Americans don't like to fail. And they don't like to fail safety trainings in particular. They don't want to make things too hard. They want to make you feel good about yourself. Germans don't care, right? Germans are just, well, if they fail, then they have to do it again until they pass. And that's why I know what the order is to wash your hands if you work in the wet labs at the European CXFEL. Because it's really hard to remember and they make you do it over and over and over and over again before they let you on site. So just something to bear in mind when you're thinking about your cyber security training. Yeah, safeguard against user software memory leaks. I once, after a 16-hour shift, went to a piece of code, commented out 1 line. I was just annoyed. I was constantly putting something out into the terminal and I didn't want it there. I just wanted it to run in the background. So I just commented out one line. I commented out the wrong line. Yeah. Next thing I know, the system's really sluggish and it's not barely responding. I'm getting really annoyed. So what do? This relates to the last point on here. Users wreak vengeance on facilities for cyber issues. I contact their computing department. I'm like, your system is really sluggish. This is not working. I cannot keep up with the data. Can you please fix this? And they're like, well, your working directory is 80 terabytes large. Yeah, I walked away with my tail tucked between my legs. I felt really, really bad. But I mean, this is software I use all the time. I trusted it blindly. I did not think that I commented out 1 line lower than I expected. So it happens. And that's why, remember this, users will abuse resources if they can access them. Very often, because people know me, I'm around a lot. I'm like, oh, I'd like to actually look at the data 1 step before you usually give it to us. Can we do that? Yeah, sure. Here are the access credentials. Do you think I will use it in the next experiment again? I will. And the same thing goes with computing resources. They're like, oh, you're having trouble logging in. Well, you can always use this node to log in. Yeah, now we always use that node to log in. So be very careful. The road to hell is paved with good intentions. We can break the unbreakable. We always can. If you think we can't find things to create memory leaks and bring down an entire facility, we can. We also inadvertently delete things. Been there, done that, data disappeared, had to redo it, or once even not recoverably. So yeah, these are just things to keep in your mind when you're protecting yourself from us. And I'm actually going to give the last word here to Winston Churchill, and it's actually the last word of the panel, I realized, before questions start. And he said, unteachable from infancy to tomb. So let's see if you guys agree with that, since we just all told you all the mistakes we made. So let's see if you take something away and make them again, because this is the first and main characteristic of mankind.
Okay, so let's start with questions, maybe to our amazing panel. Thank you very much for your talks and questions from the room. Mike's right.